So if we want to draw the reciprocal of a particular function, okay, things to notice. Well, if the original function is equal to 0, so an x-intercept, then my new graph must be undefined, because I'll end up with 1 on 0. So there'll be, well, quite possibly it's going to be a vertical asymptote. That'd be on most situations, but there's also possible it could end up with a point discontinuity depending on what we're turning upside down, but we'd be expecting a vertical asymptote. So here is random graph. So with random graph, I've tried to put every sort of possible feature I could think of there. I've got turning points, I've got horizontal asymptotes, I've got vertical asymptotes, and so on. So each of those x-intercepts will become vertical asymptotes. At least I'm thinking vertical asymptotes at this stage, but we know it's not going to exist at those x values. The reverse would also have to be true then. So if the original function is going to infinity, so approaching an asymptote, if I turn it upside down, my new graph must be going towards 0. So we end up with an x-intercept sort of. So my vertical asymptote there becomes the x-intercept sort of. You'll notice I've made it as a hollow circle. If we were to draw the reciprocal of the hyperbola, y equals 1 on x, you'd think we'd draw the line y equals x. But it's different to the line y equals x, because we're saying the reciprocal of this graph. So what I'm getting at is, if the x value didn't exist in the thing we're turning upside down, it can't all of a sudden magically exist in the new graph. And so that's why our x-intercept over here becomes a point discontinuity rather than x-intercept. It didn't exist in the original graph that we're turning upside down, so it can't magically exist. I can't substitute into 1 over function x, because I can't substitute into function x. Okay, well 1 is always a good point to look for, because when you turn 1 upside down you're going to get 1. So each of those y values of 1 will stay. Same with negative 1. And my horizontal asymptote there, I don't know exactly what it is, but I know it's a number smaller than 1. If I turn a number smaller than 1 upside down, I'd get a number bigger than 1, so I've moved it above 1. Okay. Here's an interesting thing that happens with reciprocals. When the original graph is increasing, the reciprocal should be decreasing, and vice versa. The sign's not going to change. Turn a positive upside down, you still get positive. Turn a negative upside down, you still get negative. So here, I'm just going to shade in the regions that I know this curve's going to exist. And here's my logic behind each of these shadings. So the original graph, working from left to right, we start off with a graph that is above the horizontal asymptote and below 1. So when I turn it upside down, it goes above 1 and below the asymptote. So basically we're reversing what happens. So after 1, it then goes above 1, but cuts the asymptote. So therefore my new one should go below 1 and should cut the horizontal asymptote. There's our x-intercept, sort of. We then go below -1, so it should be above -1. From there we go above -1, so it should be below -1, and so on and so on. And so that's how I get all these different regions that we're going to go in. There should be enough to try and draw a sketch, but stationary points are interesting too. If I was to differentiate 1 on function x, so the reciprocal rule if you like, minus the derivative on the function squared. So what does that now tell me about the stationary points? Well, f dash x would equal 0 on the original graph. So on the new graph, the derivative is still going to be 0, because on the top of the fraction you've got minus f dash x. So at those x values you will still get stationary points, is basically what that's saying. Alright, let's draw it. Voila, we end up with something like that. So I'll just get rid of that so it's easier to see. So there's our reciprocal graph. We turn it upside down. So they're all the sorts of things you're looking for. Okay.